Hello everyone, I'm Yi Junli from Peiyang University. Today I'll introduce our paper, OpenRDW, a redirected working library and benchmark with multi-user learning based on functionalities and state-of-the-art algorithms. Nowadays, with the increasing popularity of virtual reality applications, more people are willing to experience VR in room-scale spaces. When experiencing this immersive exploration, free movements in virtual environments are essential. However, traveling in the large virtual space can be highly constrained by the limited physical tracking space. Therefore, some effective locomotion techniques such as teleportation, walking in place, and redirected working were proposed to offer better VR experience. Among these techniques, RDW can provide a high natural feeling of working by introducing imperceptible manipulations to guide the user away from the physical boundaries, which enables users to explore a larger virtual space. For example, when a user plans to walk along a straight path in the virtual environment, the virtual camera could be slightly rotated so that the user unknowingly compensates this rotation by walking along an arc in the real world. This virtual rotation speed is usually controlled by parameters called gains. A taxonomy of redirection involves three major gains, namely translation, rotation, and curvature gains. To mimic the natural working process in the real world, the gains should be constrained within certain detection thresholds measured by user studies. Redirection controllers are specific algorithms which determine how gains are applied to steer users. Subtle redirection controllers steer users imperceptibly, including steer to center, controllers based on artificial potential fields or reinforcement learning. But sometimes it is still possible for users to reach physical boundaries, which should be corrected by overt redirection controllers like 213. To reduce the complexity of deploying RDW for VR developers, software libraries such as the Redirected Working Toolkit were developed to offer basic program interfaces for algorithm design, working simulation, and data logging. But till now, there are still very few released open-source RDW platforms, and more new features can be supplemented to handle complex application scenarios. In this work, we present OpenRDW, an open-source library and benchmark for developing, deploying, and evaluating RDW methods. OpenRDW contains two parts, library and benchmark. The library offers hierarchical classes, so users can highly customize the RDW controllers. It's also convenient to do experiments and visualize the working process. Statistic results will be automatically exported. The library also supports reinforcement learning-based methods. The benchmark includes multiple testing conditions such as diversified tracking spaces, walking paths, and RDW techniques. We implemented the OpenRDW library as a Unity 3D package for prevalent use in academia and industry. The architecture contains several basic modules and components. The movement component reads data from an input device or a predefined path to drive its avatar. Predefined paths are mainly used for automatic simulations, and these virtual paths can come from procedural generation and real-user working experiments. Redirection component receives the information of virtual scene and avatar movement to compute gains in real time. This component contains multiple candidate redirection controllers and determines which will be used according to the situation. For example, if the user is around the obstacles or boundaries, resetting controllers will be evoked to avoid collisions. Otherwise, subtle redirection controllers will be called for imperceptible manipulations. Our redirection component also offers support for reinforcement learning methods. We also implemented the state-of-the-art reinforcement learning method as a built-in exemplar. The global configuration module defines data structures to store gain thresholds, tracking space, and other parameters. This module also controls the beginning and the end of an experiment. An automatic simulation can be executed in two modes. In the standard mode, The simulation process is rendered and displayed at the target frame rate, which helps researchers to observe the simulation clearly. In the backstage mode, the rendering pipeline is omitted to accelerate the simulation process, which is useful for fast batch testing. The tracking space component defines the data structure of the physical tracking space. There are two predefined types of tracking space: size-varied tracking spaces and shape-varied tracking spaces. Users can also customize the tracking spaces for testing. The visualization module visualizes the working process. There are two modes for visualization. In overview mode, the top view of the whole tracking space will be shown. Redirected paths of different avatars are highlighted in corresponding colors. In following mode, a user-specified virtual avatar will be followed. The target working paths and redirected paths are highlighted in blue and red respectively, and paths of other avatars are temporarily hidden. In order to analyze the performances of RDW methods under different conditions, diverse information and metrics are recorded by the analysis module. This module also supports high-quality exportation of the simulation process videos and working trajectory images. To support multiple real-user working, OpenRDW library integrates Photon Unity networking tool for network connection and synchronization. This video demo shows two HTC Vive users working in the 6 meters by 6 meters physical tracking space. A 1 meter by 1 meter square obstacle was set in the middle. Based on the library, we constructed a benchmark to evaluate RDW methods via simulations. There are two types of tracking spaces in our dataset. The first type is size-varied tracking spaces. Each space is in square shape and 4 types of side lengths are used. The second type is shape-varied training spaces, aiming to test the scalability of RDW algorithms in complex application scenarios. In our dataset, 6 varied shapes with 3 obstacle settings are designed. To make the testing data diverse, the virtual paths are obtained via procedural generation and real user working. There are 6 types of procedurally generated paths. Among them, random turn and 90-degree turn are generated randomly. Other paths are generated following certain patterns. We also collected paths worked by real users. These paths are more diverse because each user's working data could be different in both trajectory and working speed. There were 2 tasks. The first task was a waypoint collection in a simple virtual scene. Participants were asked to follow the procedurally generated green spheres. The second task was prop searching in 2 virtual scenes. The positions of virtual props are marked with stars showing on the right figures. The office scene contains 10 trophies, and the store scene contains 10 sandwiches for participants' collection. The participants were asked to collect all of the virtual props by searching and reaching them using Vive controllers at their normal working speed. Currently, this benchmark integrated 10 RDW controllers. The methods S2C and S2O represent the classic reactive controllers. Zigzag represents the classic predictive controller, which can fold a sawtooth-shaped virtual path into a back and forth pattern. Besides, there are 4 APF-based methods to represent the state-of-the-art reactive controllers, and Steer-by reinforcement learning represents the state-of-the-art predictive controller. Regarding resetting controllers, 2-1 turn is the most common resetting strategy. While the APF resetting makes the user physically rotate towards a vector calculated by artificial potential fields. OpenRDW benchmark contains a variety of combined conditions of tracking spaces, virtual paths, and the number of users for adequate evaluations. Here we show a few representative results. All baseline methods can use 2-1 turn as the default resetting controller. Additionally, APF-based controllers can combine with the APF resetting controller as alternatives, which are denoted with an asterisk. For size-varied tracking spaces, Results of recess and distance between recess are shown in the figure. For shape-varied tracking spaces, we only evaluated 8 combinations due to the scalability issues of applying some of the controllers. One visualization example of the same virtual path redirected by 3 methods is shown on the right. For multi-user working, results of recess and steering rate of curvature gain are shown in the figure. For more details and statistical results, please refer to our paper and supplementary materials. To conclude, we proposed OpenRDW, which is an open-source library and benchmark for faster development, deployment, and evaluation of RDW techniques. It is beneficial to the whole community and supports both commercial and academic use. It also supports novel features like multi-user simulation and state-of-the-art methods. In the future, we will test OpenRDW on more VR devices. It is also worthwhile to compare different approaches with user studies. Moreover, we will improve the UI, simplify the deployment procedure, and integrate more state-of-the-art RDW methods. Because OpenRDW is a growing project, we will keep adding new features and welcome researchers to contribute to this project together. Thanks for watching.